This is section 5.1 on the topic of coordinate vectors. The idea of this section is that we're going to explore something called coordinate vectors, which it turns out allow us to describe the elements of any real finite dimensional vector space using only the elements, the vectors, in Rn. So keep in mind, when we say a real finite dimensional vector space, we mean finite dimensional, that is, the basis for the vector space has finitely many vectors, not infinitely many, and we're associating these with real scalar values. So that's really the value of this lesson, is we're going to see how to express any of these many types of vector spaces, or the elements of these vector spaces, using just the vectors in Rn. This is going to be a big development for us. So let's start with the definition here, which we're actually going to modify just a little bit, but I want to show you how how your textbook describes this before we see a little modification to the notation and terminology we use here. So let's look at your book's definition for this. The definition we want to go with is let U be a vector space with a basis B consisting of these vectors U1 through Un. So remember, a basis is just a standard way to represent everything in that vector space uniquely. And let U be any vector, right? Let vector U be any vector in this vector space. Then, by the definition of bases, we know right away that there exists a unique set of scalars, A1 through AN, such that this linear combination of those basis vectors, using the scalars A1 through AN, produce U. Right? There's only one set of scalars, A1 through AN, that will give you U in a linear combination of these basis vectors, U1 through UN. So we are going to, with that setup, define the column vector U subscript B for the basis name, but it's this column vector filled up with just that unique set of scalars, A1 through AN. Right? This is called the coordinate vector of U relative to that basis B. And the scalars inside this coordinate vector, we just call those the coordinates of U relative to B. So when I'm referring to one of these coordinate vectors, I may speak a little bit loosely and just say this vector is the coordinates of U relative to a certain basis. I really mean it's the coordinate vector. Its components are the actual coordinates. A little note here, we are going to use column vectors to represent all these coordinate vectors. I suppose you could represent these all with row vectors, but it makes some of the mathematics work out, or requires you work out some of the mathematics differently, maybe in slightly more complicated ways in some cases. So we're going to use these column vectors just for the sake of convenience, just as a convention here. It's pretty common. So now on to a note about this definition. I mentioned we're going to modify how we talk about these things a little bit. This is your book's definition we've just run through. But let's talk about notation and concepts a little bit more here. If we do have one of these coordinate vectors, the order we write these coordinates in actually does matter a great deal, right? It tells us which scalar goes with which vector from the basis to make up this linear combination. And so really, the coordinate vector is not just relative to any basis, it's relative to a given ordered basis, where the order that we're writing those vectors depends on or determines the order that we write these coordinates in the coordinate vector. Right? So let's look at this a little more. Given any basis, a set of vectors B1 through Bn, the basis here, that is just a set, right? And a set is equal to any other set having that exact same collection of vectors, regardless of the order they're listed in. So this set, B1, B2, B3, all the way through Bn, that would be the same if I wrote that set down in with any other order for those vectors. A set really doesn't care what order you write these in. So we need to specify not really just a basis, but an ordered basis, which we'll denote with sort of a script B here. We're going to denote that with these square brackets instead of these curly braces here. And the order we write the vectors in these square brackets will be fixed, right? We'll say that this ordered basis here is not equal to any other ordered basis unless it's the same exact vectors in the exact same order. So when we are going to write down a coordinate vector, it will really be with respect to or relative to an ordered basis, not just any old basis, which doesn't care about an order. Ordered bases care about order. So that's what we're going to really say these coordinate vectors are relative to, an ordered basis. Okay, now that I've said ordered basis about 500 times, let's see what's next here. Often in this discussion, it's pretty common to talk about two different ordered bases for a given vector space. We're going to denote those just by b and b prime, where the prime again is not like a derivative or anything. It's just a marker saying this is some other ordered basis compared to the original one. The prime is just a marker saying it's a different ordered basis. And if you have a vector u in that vector space, we're going to denote its coordinate vector relative to the ordered basis b as really what this definition in your book said, u subscript basis name b, right? So u subscript b. And the coordinate vector of u relative to b prime, well, you just put a b prime for your basis name in the subscript. Probably that's not too hard to grasp, but this idea that we do really need to specify that we're talking about ordered bases, that's the big message of this little block here. So let's see some examples. Let's let u equal -2, 3. That's a vector in R2. And let the ordered basis B1 be this ordered set of vectors 1, 0, 0, 1. We want to find the coordinate vector UB, right? The coordinate vector, I should say UB1, right? With respect to basis B1, ordered basis B1. So what are we really trying to do? We're trying to take this vector U, and we want to find scalars, right? We need to figure out how to write U as a scalar linear combination of these basis vectors. So we want to find scalars, I'll call them A1 and A2, such that our original vector U, which at the top of the screen you can see is -2, 3, such that this thing equals A1 times the first vector in the ordered basis plus A2 times the second vector. And in this case, this is very easy to do. All we're going to have to do is combine everything together that sits on the right side of this equation. So for example, the A1, we can take that through this vector. Fix this. And that's just the vector A1, 0. Take the A2 through this vector, right? Bring that scalar in. And we just get this. And now this is just a couple of vectors we can add together. This is just A1 plus 0, which is A1, plus, 0 plus A2, which is just A2. So at the end of the day, what do we have? -2, 3, what we started with way over here, equals A1, A2. That vector of scalars. So this is easy, right? And what made this so easy is that the basis, the ordered basis we're looking at, is the standard basis, right? This is just this little red vector I've drawn horizontally here in the unit vector there. That's our 1, 0. The vertical red vector is just the 0, 1. So this is the standard basis. It's like your I and J vectors. But we have our answer. We know what our A1 is. That must be -2, and A2 must be 3. So in this case, we can write the coordinate vector of U relative to basis B1, ordered basis B1. It's -2, 3. Okay, and so we're seeing that we did write it as a column vector, but otherwise, since we were expressing this in terms of the standard ordered basis here, the coordinate vector looks just like the vector itself expressed in R2. This thing was already expressed in terms of this basis. That's what we're really seeing. The coordinates didn't change. So visually, what are we thinking? Let's see if we can diagram this out in our picture here. We'll use a different color. We're saying to get to this vector -2, 3, which I've drawn in black in my picture, right, points from the origin to the point -2, 3. It says I need to go -2 copies, right? -2 copies, that's my A1 value, in the first basis vector direction, the 1, 0, the horizontal red vector. So if I went negative 2 copies of that, that would be not forward in the horizontal direction given by that red vector. That's backwards, 2 times as far. Right? That's negative 2 times 1, 0. 1, 0. And it says after that we have to go 3 units, or 3 times as far as this 0, 1 vector. So the vertical red vector, we need to go 3 copies of that in displacement. So 1, 2, 3. Okay, that's 3 times 0, 1. And what it's saying over here, right, the A1 value we found is negative 2. The A2 value we found is 3. So we're really saying if I add this vector, the little vector of length 2 in the negative x direction, if I add that to the 3 times the 0, 1 vector, that should give me my u vector back, my black vector. And we can see this makes sense. By graphical addition of vectors, I can see, yeah, adding this blue vector that's horizontal and the blue vector that's vertical, that would give me exactly this black vector we started with. Right. So we're just describing how do I amount to the same displacement as this vector, just in terms of scalar amounts of each of these basis vectors. Right? Negative 2 copies of the first one plus 3 copies of the second one is the same as this vector, negative 2, 3. Okay, so let's do another example here. We found our coordinate vector there. Let's now look at the basis 0, 1, the ordered basis 0, 1, 1, 0. Notice this is the same set of vectors in opposite order. Here we're seeing why it's so important to specify ordered bases. So this is going to be easy though, right? We can do this without any work. We have found how to write our original u vector. It's the same u vector we're going to use down here. I didn't specify, but it's the same negative 2, 3 vector. We've already seen how to write u as a linear combination of 0, 1, and 1, 0. It's just 3 times 0, 1 and negative 2 times 1, 0. Right? So we've already done the work. We know we're just thinking of things with opposite order. So I can just write this down. This vector u, we know it's 3 times 0, 1 plus negative 2 times 1, 0 from what we previously did, right? Well, that tells us the first vector in our ordered basis is 0, 1. The scalar we need in that linear combination of those two vectors, the scalar attached to 0, 1 is 3. The scalar attached to 1, 0, is the negative 2. And this should make good sense. All we did was flip the order in our basis, so we should notice the coordinates just get reversed in order. Instead of negative 2, 3, now it's 3, negative 2. And the picture is exactly the same as the picture up here, because in this picture, we had no way of specifying which basis vector was considered first in the ordered basis. So our picture is going to look exactly the same down here. We're still just taking 3 copies of that vertical red vector, negative 2 copies of the horizontal one, and saying those add to equal the original black vector. So let's do one that's a little more interesting. That one just shows you really the need for this order on the basis. Let's look at this one real quick. In this one, notice our ordered basis in this case is nothing like the ordered bases we've already worked with. Right? Completely different vectors. Order doesn't matter since they're different vectors, but yeah, this is a completely different basis. And I've drawn the same sort of situation. We have these 2 red vectors. The short one is the 1, 1 vector. The longer red vector is the 1, 6 vector. And we're asking, how many copies of this red one, the short red one, and how many copies of this long red one must be added together to make the black one, right? Our original negative 2, 3 vector. Well, we'll set this up the same way as before. We just still want to find those scalars in the linear combination of these basis vectors. Just a sec. That make our vector negative 2, 3. So let's see if we can do this. Same way as before. We just set up a linear combination of these basis vectors. I'll still use A1 and A2. You could use any symbols here you like. Oops. There we go. And now again, we're just going to put all this stuff on the right side together. In the first components on the right side, I have one copy of A1 plus one copy of A2. In the second components on the right side, I have one copy of A1 plus 6 copies of A2. And we know at the end of the day, this has to be negative 2 in the first component and 3 in the second component. This gives me a system of equations I can solve. The first components on left and right sides of the equation must be equal, and the second components on left and right sides of the equation must be equal. Okay, so now I just need to solve this for these scalars. You might pack this up into a little augmented matrix or something. Reduce it down. I'll do these steps for you. You can check what I get here. I think I get, let's see. It looks like this is what I get when I work it out. You can check this step. I encourage you to check this step. Check my reduction here. But this would imply that A1 is negative 3 and A2 is 1. Okay, so let's see if graphically this makes sense. Or I guess right away, let's just write down our coordinate vector. Oops, sorry. My eraser's not working right. There we go. Let's see if we can write this down. It's just our coordinates, A1, A2, in a column vector. So visually what's happening in this case, well, again, we have the same sort of reasoning as before. We need negative 3 copies of this short red vector, the 1, 1 vector. So instead of going in its direction, we'll go negative its direction and 3 times that vector. There's 1 copy, 2 copies, 3 copies. And then we need 1 copy of the long red vector, so just this guy, already as it is. We're saying if we add those, we should get the black vector back. And this looks like it's perfectly working out, right? If I add these graphically, from here I'd want to repeat from the tip of the negative 3, 1, 1 vector, I'd want to kind of repeat this 1 times 1, 6, the other blue vector. And from there, it would actually put me right here. Adding those two together graphically would give me the u vector. It's negative 3 times the first basis vector plus 1 times the second basis vector. That's why our coordinates are negative 3, 1 relative to basis B3, ordered basis B3. Okay, so let's go on and see one that's a little less concrete maybe for us, right? That last one all occurred in R2 in the plane where we can easily imagine with pictures how we're breaking down one vector in terms of others. But now let's look at an example that's on maybe a more abstract sort of vector space. Let's let u, the vector u, in P2, the space of second degree polynomial equation functions. So these are your quadratic functions, right? Let this u be defined by u equals 4x squared minus 3x minus 1. I've written it parenthetically under this as f instead of u, so you're really thinking of this as a function. But really to emphasize the vector space point of view, I am referring to u as a vector in the main text here. So over here where I wrote up the definition of u, I'm writing f of x equals this function. Okay, so we want to express that vector u, this little function, this quadratic function, we want to express its coordinate vector relative to this ordered basis for P2. The ordered basis x squared x1. This is the standard basis for P2, so this becomes super easy again. Notice our vector, get back to black ink there. Notice our vector is already written as a linear combination can even make it clearer, of these basis vectors, even in order for us, right? As nice as it could be. So that tells us right away the scalars we need in a linear combination of these ordered basis vectors to make our vector u. Our vector 4x squared minus 3x minus 1 is exactly 4 copies of x squared plus negative 3 copies of x plus negative 1 copy of 1. There are our coordinates, right? Easy enough. And again, this is only made so easy by the fact that this was a standard basis that we started with. Easy enough. And so what about the next one here where our ordered basis is 1x squared negative x? Well, I claim we don't have to really think too hard. We just notice how these basis vectors have been rearranged or maybe scaled relative to the original ordered basis b1 up here. What was in the last component should go in the first. What was in the second component, negative of that should go in the last. And what was in the first component, that should go in the second. Right? All we've done is mixed up the order and maybe flipped a sign, but I think we can just kind of stare at this for a second and see how that's going to change our coordinate vector. Right? What was here should go in the first component now. So negative 1 is in our first component. What was, let's see it. What was here, what was on the x squared, now that goes in our second component. So that's our negative 3. Oh, sorry, that is our 4, right? The first coordinate went with x squared and b1. So we need a 4 here. First component went with x squared, now it goes with second component x squared. And finally, what was in the second component, that negative 3 over here, we want negative of that to account for the fact that the basis vector already has that negative for us. So we'll just put a positive 3 there. We're done. Good enough. That's all we need. And again, the next one's going to be a little more complicated, but I just wanted to show yet again the importance that there's an order enforced on these bases before you write their coordinate vectors. So let's look at this last one down here, B3. Same idea. We're just writing that vector, u equals 4x squared minus 3x minus 1. We want it to be some linear combination of these basis vectors. Right? Well, do what we've done in every single other example we've seen today. Expand the right side. Just combine like terms, put everything together that you can. And what do we have? We have a1x squared. What's on the linear x? Looks like we have negative 1 copy of a1, 2 copies of a2, and a copy of a3 attached to the linear x. Right? Just multiplying, there's your negative a1, there's your 2a2, there's your a3. And the constants, let's gather up the constants. That's easy. We just have negative a3 for our constants from here. Everything else has an x. We've seen this process before, right? All of this stuff should be pretty familiar. Writing a given vector as a linear combination of other vectors. But we've seen how to do this. Now we just equate coefficients of like powers of x on both sides of the equation. So for example, we can say, looking at the x squared powers, on the right side we have an a1, on the left side we have a 4. Equate those. If I look at the linear powers on both sides, the coefficient on the right side is negative a1 plus 2a2 plus a3, and that's got to equal negative 3 on the other side. Finally, so that was x to the 1 power. The constants, that's like x to the 0 power. We have negative a3 on one side, negative a1 on the other side. So we have immediately quite a bit of information here. We know a1, a3 is trivial, a3 is 1. We should be able to use those two values to find a2 in the middle equation. So what do we have? It looks like -4 plus 1. That's -3 on the left, -3 on the right. Those cancel. You have A2 must be 0. And from there, we're home free. Those are our coordinates, right? Those scalars we needed in a linear combination of the basis vectors to make the u we started with, those scalars are the components of our coordinate vector. 4, 0, 1. That's the coordinates of this vector u relative to basis, ordered basis, B3. Okay. So that is it for this video. We will pick up in the next video to finish this section.